Shoot that 42. Got it. No, I don't have it. What are we trying to do? Find the following average values. So you guys, I'm sorry for being clunky writing this down. The author is asking us to find the average distance squared from the unit disk to the point 1, 1. Pictorially speaking, here's my unit disk. And here's a point 1, 1.
Wait.
Yes.
So the unit disk doesn't go one out, or
That's more than 1 hour.
oh, okay. I get it. It's just, never mind.
Oh, I see. Yeah, here's my tick of 1 on the x-axis. Here's some y-axis.
Okay, that helps.
How do you find the average of any y then?
Just take
Divide by 2. Divide by. I just didn't hear.
the area.
I didn't divide by the area. And so I think I'm going to have an integral. That's 1 over the area times the double integral over that region, the surface of my disk, of, gosh, I don't know. How do you compute the distance between 2 points? I don't know. How do you compute the distance between 2 points? Square root of some stuff. Oh, but it's the average distance of square. It's the average of the square distances. I won't put the square root. But I do think I've got my x minus 1 quantity squared plus my
minus 1.
Are you guys okay with this? Be honest. Oh, you're not.
I mean, that's just a circle. Right?
See, I think this has nothing to do with the circle. I think with everything inside my brackets simply comes from this. That the distance between any 2 points P and Q in the Cartesian coordinate system could be interpreted as
square root of P squared plus Q squared.
Exactly.
No, I knew where that was coming from. Yeah,
Okay.
that part was pretty straightforward.
What's next? Well, just a section 11.3, so you can assume that the author intended for you to rewrite everything in terms of polar coordinates. So let's not go inside Winogrand's position. Let's do something different. Let's just talk about that region. Now talk about the region. I think my bounds of integration go from, is that -1 to 1 and -1 to
No.
No. If I'm going to write this in polar coordinates, not that I did anything wrong, I didn't. But if I'm going to write everything in terms of polar coordinates, I think my r values are ranging from
0 to 1.
but my theta values are ranging from
0 to 2 pi.
201, 2 pi. Yes.
I guess with the whole theta value, don't we kind of want to get the closest to the farthest points? So like the farthest distance isn't 0, the closest distance isn't 2 pi. Couldn't you do like pi, what is that? 5 pi over 4 to pi over 4? And then that would give you the farthest minus the closest. Is what I'm saying making sense? I guess.
So Caleb, you asked. I thought you asked about this question.
Oh, yeah. I mean, what are we doing in general?
Okay. Anybody else? Anybody?
You didn't answer for the rest?
I know, I want to see what anybody else wants to say.
Oh, okay.
R cosine theta and R sine theta for.
If you insist. So what would that give me? Is that an r squared minus 2? I can't read that, can you? I said r squared minus that 2r cosine theta minus 2r sine theta. Oh, yeah. Is that a plus 2? Anybody else want to say anything?
Is that just substituting r cosine
Yeah,
for
it's-
cosine?
Yes, that's all it is. And I expanded by negative distance.
Oh, also, does it matter if we do minus that or exponential?
Completely irrelevant, because when you square the darn thing, you're not gonna see the difference anyway. You get exactly right. And, am I missing anything? Oh, I forgot the DRB beta, didn't I?
RDR.
Plus an extra factor of R because we're looking at the arc length on that little wedge. Is there anything else missing? Yeah, I forgot the area. So let me come up with an integral. Do you guys want to use double integral or single integral? What would you prefer to use? I'll do the work. Do you want a single or double integral?
Geometry?
Yeah, nothing. How about just stating the answer? I think the area of that region is nothing more than,
Oh yeah, pi squared. I mean, pi equals 1.
oh, thank you. It's just pi, just pi.
I don't know why, I thought pi r squared, but I was like, you can't have an r, so I figured I just took the r out and squared the pi.
Well, there is an R, it's just Y.
In my head, that's not process.
R is 1.
Yeah.
Yeah, I'm listening.
Why isn't there a 2 on top? Should be,
Why is there a 2 on top?
well, why isn't there there of the 1 over A?
Oh, you mean over here? My apologies. It's because I was computing the area of this region, it's just pi r squared. There it is. Matthew, is that okay?
Because it has a 2 on top on the thing, on the book. I know, I'm just trying to get the general formula.
Yeah, just tell me if I'm missing it.
That's fine.
All right. Okay. Oh, by the way, do you guys mind if I don't finish?
You still haven't answered the one question that I had.
Oh, you know, I completely lost it. What was it, Eric? No, you did say something, I wanted everybody else to talk, and nobody said anything, so I've lost track of what your question was.
Okay. My question was, why can't you do it from pi over 4 to 5 pi over 4? Because I guess the way I look at this, it's really not going to give you the longest distance between the two, because it's, you're trying to think of a way to actually say what the thoughts that are coming in my head. That's really the only way I know how to do it. Would you have to multiply it by 2 if you were to do that? Is that?
Only because of point 1, comma 1 is positioned so nicely, yes, I guess you could do that. I'd be a little nervous if point were located somewhere else. But yeah, I don't mind you doing it in that way.
What is the question really asking?
And I just erased it, sorry. And I didn't do a good job writing it.
On the picture, so if we're taking a point in the circle
So watch my colors.
and another point in the circle and adding up all those distances and taking the average,
And then divided by the area, you get the average. So for
Okay,
example,
all
here's
right,
one
so
of the
that's what-
values. That distance, call it D1. Here's another value, here, I'll call it, whoops, hold it. Yeah, it's dry erase. Call it D2. Now, I know I got infinitely many distances to add together.
Right.
But the point is, with integrals, I can come up with the average of infinite collection of distances.
okay, so we're just taking every single point in the circle, drawing a line to 1, 1.
Comma 1.
And then taking the average distance. Okay, so
I agree.
that is what we're trying to find out. What is that used for?
It's just a
Exercise?
contrived example.
Okay. Because I don't know if it has any practical purpose, probably somewhere in engineering.
When I was reading up on it, they were talking about how you could use it for galaxies, calculate the average distance between certain planets if you had so many.
Oh, I can see that, yeah, good point, I can see that, that's a good application. But I think that would more come into play of looking at the average of the distances, not necessarily the square
So
distances.
it's a lot more complicated.
Yeah, because the integration process is more nasty, I agree. And by the way, that's why the author did look at the square of the distances, it's just easier to compute. Okay, you guys, I'm gonna change the name of the game.
Does that picture go into 3 dimensions at all, as far as what we're doing with double integrals? Or?
I guess you can interpret it that way. I mean, look at this interpretation. And don't look at the application. I know we're looking at the average and the square, just all that kind of garbage. But if you guys can imagine that this is a surface in 3 space, let's see equal to it. If I wanted to, I can rewrite this as a triple integral. I'll just put the third integral in it. It's just what the integrand's position is going to be
TV.
1 dv or dv. But my bounds of integration are going to be from 0 to this nasty business as the upper bound for that innermost interval. I can interpret it that way. Does that make sense?
Yes, but I guess I'm more saying we interpret double integrals as given as volume in a lot of cases. How are we interpreting it in this situation, and how does that work with those different interpretations?
Say that again.
So we use double integrals we can interpret it as volume in a lot of situations, right?
Yes.
So how does that match with this how are we interpreting this, and how does that?
And here is that interpretation. You could, oh, I see your point.
Yes.
If you treat this, not writing as a triple integral, treat this as the output of some function z, you can think of the entire double integral right here as representing the volume underneath the surface, z being this garbage, over that particular region R.
Right.
So
But how
you-
does that help us get us distance, I guess is my question, average distance?
It doesn't. This is just an interpretation of coming up with the squared average distance. That's all. And it's not pictorial, but, well, I shouldn't say that. It is pictorial, but not in terms of computing volumes. Better. All right. If it is, you guys, I'm going to draw another pretty picture. Here's my x-axis. Here's my y-axis. Here's my z-axis. And I know to locate a point in the x, y, z coordinate system. I walk along the x-axis a certain distance, walk along the y-axis a certain distance, walk along the z-axis a certain distance, but I can do something different. What if I decided to locate a point in the xy coordinate plane and travel there by using my polar coordinates? I will look at it at a certain angle, walk a certain distance r, but then to get to this point, I'm going to walk vertically up z units. And I think it's going to be locate a point in 3 space. I'm just going to use different representation for its coordinates. How about r as in betas and z's? So if I were to do this, it's just a different way of representing this location. I'm going to give it a name. I'm going to refer to this as a cylindrical coordinate system. I like to use the word cylindrical only because if you were to rotate this around the z-axis, you do get a cylinder. That's what we refer to as a cylindrical coordinate system. And I maintain...
Say that again, please.
Yes. All I'm saying is, I refer to this technique of locating points in 3 space as my cylindrical coordinates. You guys, there's nothing extravagant about this. It's nothing more than looking at polar coordinates just extended in 3-dimensional space.
Did you already finish triple integrals, or were we just done?
I thought we finished triple integrals, didn't we?
No.
You said that there was still more that you needed to do on it.
Lecture on.
I
You didn't decide
apologize.
homework yet.
I mean, it seems easy enough.
Really?
But you're-
Well, that embarrasses me. I don't remember what it said.
You said you didn't do enough examples to assign homework and that you needed to do more today.
Gotcha. Okay, I will. But I started. I just finished it. Yeah. And everybody, I think that means when it comes to a triple integral, instead of having my bounds for x, y, and z, it's going to
But
change.
go back, the part that was something about a cylinder, and that's why it's called cylindrical, that part I need to repeat.
I refer to these cylindrical coordinates only because if you were to rotate this around the z-axis, I mean, it basically behaves like a cylinder. And with most surfaces that are described in a cylindrical fashion, making certain substitutions is going to make my life really easy. Now, you guys,
Does Z have to be constant for the cylinder?
does what have to be
Does
constant?
Z have to be constant? I mean, if Z, because we talked about spherical coordinates the other day, and if Z is a circle, then you get like a sphere, right? If the function for Z is a sphere.
Even if z equals something that where the surface represents a sphere,
Yes.
then
Then you get
spherical
spherical coordinates, so does Z have to be constant for cylindrical coordinates?
it does not. But do this.
I'm sorry, not constant, but I'm trying to.
Dependent.
You guys look at all the points in the input. If I allow r to be fixed, allow theta to range from 0 to 2 pi, allow z to range from negative infinity to infinity, aren't you going to get that unbounded cylinder wrapped around, centered about the z-axis? So in sensitizing, but r is constant. No, I'm saying if r were constant. If it were, then I get a picture of the cylinder. But in general, what I'm gonna do is use this new coordinate system to actually evaluate integrals. It's just that when I transfer to cylindrical coordinates, it makes the integration process easier. That's all. So you guys allow me.
Is this just like a step up from the other, from polar coordinates?
That's all it is. The only thing that's changed is it got the z in there, but the z is the same z that you see when you evaluate standard triple integrals.
So this is comparable to double integrals putting them into polar coordinates, now triple integrals
Absolutely.
putting into cylindrical coordinates.
Although
Okay.
this is only a small step in this example, as I'm just adding the z.
So
Nothing
could
else
we-
changes.
Could we potentially do an n number of integrals for an n-dimensional object?
Yeah.
Can you imagine sitting again? I'm sorry, I'm just tired. I didn't catch all that.
Can we deal, so let's say we have a four-dimensional object and we have to do quadruple integrals, right?
You could, you don't have to, yeah. There's nothing wrong with jumping into higher dimensional space.
Is there a-
So if you're working in the spherical coordinate system with these triple integrals, or the cylindrical coordinate system with these triple integrals, what would you be working with a quadruple integral?
Is there a polar
If in the
coordinate?
if you're in the integrand's position
Yeah,
with four intervals,
yeah.
and you allow that integrand to be 1, you can interpret that evaluation to represent nothing more than the amount of space in a four-dimensional object. Now, I'm being careful about choice of words, the amount of space. I mean, is that volume, is that area? Well, I have a different word for it, because interpretation of the amount of stuff within a four-dimensional object has a different interpretation.
So I mean, generally couldn't even graph something like that, right? Or
Yikes. I can. Like, for example, a four-dimensional sphere.
yeah,
I can talk about what that looks like from a three-dimensional perspective. It's just that I'd show it by taking a slice into it, and I'd see multiple layers of a three-dimensional surface. And collectively speaking, those multiple layers of three-dimensional surface will constitute the image of the four-dimensional object. Just like with the sphere in 3 space, you can think of it as cross-sectional slices of circles,
okay.
traces combined in. And typically, if we have a simple four-dimensional surface, we can represent that visually in 3 space by doing just that.
Okay.
It would be hard for me to draw one.
All right.
I'll try to conjure up some pictures and bring it in next time.
Okay.
So you guys, let's do something simple. Let's compute the volume of a sphere. What is a volume of a sphere? 4/3 pi r cubed. And I maintain if I were to compute the volume of a sphere, I'd probably graph maybe how about just half of one? How about a hemisphere? Looks something like this. Do you guys agree? Oh, by the way, what would this equation be? I said, by the way, what would this equation be?
4/6 pi r cubed.
The equation of
Well, don't you just want to look at it in the first octant too?
we can do that, but give me the
Okay.
equation anyways. It's equals something.
Yeah.
Can you be more specific?
That's what you mean.
Yes, that's what I meant. Blood's rushing out of my arm.
X squared plus y
Square root.
1 or r, or, yeah, r squared, yeah. Minus x squared, minus y squared.
Are you guys there?
Nope.
Why not? Isn't the equation of a sphere this? Well, I should say the equation of a sphere whose radius is r.
Okay.
And I maintain using triple integrals, I've got nothing more than, actually, let's just do half of it. And I think I've got the volume is twice the evaluation as triple integral. Yes.
So you just plug in cosine theta and sine theta for that, and it's like,
I was hoping you wouldn't. So I wanted to set this integral using triple integrals, rectangular coordinates, since I didn't have enough examples last time.
okay.
So let's just use standard triple integral, standard x, y, z axes. And I think my z values are going to range from 0 to
Well, what are we, asking this? 0 to r function is z, or 0 to this r function is z, which is the square root of r squared minus x squared.
beautiful.
Yeah.
I agree. That bounds for y are going to be. Bless you. Why do I feel so alone today?
Zero.
Zero R.
All right, I got an idea. You guys better check yourself down to the XY coordinate plane. I can clear the Z down already. And the XY coordinate plane, if I'm going to integrate respect to Y next, doesn't that mean I've got these nifty little red arrows in here going in the Y direction? Oh, but shoot, in the XY coordinate plane, I guess I'm just playing inside of a circle whose Y values are going to range from one extreme X to another, which are negative square root of 1 minus X squared. Oh, did I say 1? Hold on, I made a mistake. Actually, it wasn't a unit circle, it's any circle. My apologies. All the way up to the square root of, same thing but positive. Oh, by the way, numerically, just numerically, no variable expressions, the extreme values of X are going to run from,
Negative R squared,
well, negative R period,
negative R, to,
to R. I like it. I think that's how you compute the volume of the sphere, using triple integrals. Do you want to do it?
Did you forget your R squared on the dy bounds?
The dy bounds.
oh, yes.
My apologies, I certainly did. You guys, I'm being honest. I didn't come to class prepared to do this. So I've got a really honest question. I don't know the answer to it. Is this easy to evaluate?
maybe.
So Z's, then I integrate respect to Y. I'm sorry I'm so slow.
No, it's okay.
Yeah, it's not gonna be fun to evaluate.
You gotta do like trig sub and.
We could.
Yeah. Yeah, it is kind of nasty, isn't it? But you guys, only because I see some X squares plus Y squares in there, maybe this would be a good candidate to apply spherical coordinates. I say spherical, sorry. Cylindrical coordinates. Let's give it a shot. Using cylindrical coordinates. I think another name for what's the integrand's position is
R,
R,
dr,
dz, dr,
dz, d.
I will typically integrate in that order when it comes to cylindrical coordinates. And guys, I apologize for erasing the picture. Remember the surface? You had an equation, the square root, z equals the square root of r squared minus x squared minus y squared. Doesn't that now look like a square root of a big R squared minus little r squared?
Yep.
And I think my R values range from
Negative,
say that again?
well,
0 to big R.
yeah,
And my theta value is going to range from
0 to 2 pi.
yeah, 1 full revolution. Oh, by the way, that's just the area, the volume of the hemisphere. I better multiply by 2. Now here too, you guys, I'm just being honest. Is that going to be easier to evaluate? Oh shoot, that's going to be a piece of cake. Only because it is, and because you know the answer. Can we just finish and make sure we get 4 through power?
Uh-huh.
Because I think this gives me 2 times this and less evaluate. Anti-differentiate, we get r squared over 2.
1/2 R squared.
Is that what I get?
Well, if you're, well, over 2, so it's just gonna be R squared.
No, I mean, if respect to z first. So what's the antiderivative?
Oh, ZR.
ZR or R times z. Very nice. And I'm going to evaluate this from a z value of 0 to a z value of this square root nasty business.
Okay.
So can I assume that there's like the average value of a volume and that we can also change the
Absolutely.
bounds?
I agree. And I think this gives me a 2 times this integral. Hold it, I meant this double integral. And what's left over? Is that going to be an R times square root of stuff?
Or you could just do a use of really fast.
Yeah,
Save
we can
yourself
do a
some
quick
space.
easy use of, can't we?
Yeah.
And I think this transforms into nothing more than 2 times the integral from 0 to 2 pi. Well, this anti-differentiate. So that can give me a negative 1/2 times an r squared minus r squared raised to the 3/2. Hold it, I might have made a mistake. I now need to multiply by 2/3. And I'm going to be integrating with respect to, gosh, I missed a whole integral. Jeepers, I didn't even rewrite it. Is that from 0 to r?
You said already.
I did already integrate. Jeepers, I can keep track. But now I'm going to integrate with respect to, yeah, theta. I get a tad bit of cancellation in here. Excuse me. Yeah, that is a negative. Do you see where it came from? Because if I had a big U substitution, if I allow U to be big R squared minus little r squared, du is going to be negative 2r dr. And that's where I got my factor theta in. You guys, please stop me if something's unclear. And I think I can't read my own writing, so give me a moment. Is that a negative 2/3? And I think now I've got the integral from 0 to 2 pi of merely my r squared minus r squared raised to 3/2 pound. Now, integrating with respect to theta, you guys, isn't that just going to throw a factor theta in here?
Yeah.
But I'll evaluate from here to here. Isn't that just simply going to give me a negative 2/3? Times my r squared minus r squared evaluated the upper bound of integration.
No, you're evaluating theta at the.
Good, remember, I'm antidifferent with respect to theta. I think it's going to give me this right now. But I'm going to evaluate this from 0 to 2 pi.
Wait. What about your 5/2? Should be up there, or your 3/2. Sorry, your 3/2. You didn't leave your 3/2 in there.
Well, that's true, but what else did I do wrong?
That little r squared shouldn't be in there.
Yeah, I'm evaluated from here to here. I never evaluated.
Oh.
0 to r. My apologies. So let's do it. Let's evaluate. Does that give me my negative 2/3 times the integral from 0 to 2 pi? I'll plug the big R in. So you guys watch. I'm going to skip a step. When I plug big R in for little r, I get 0. When I plug 0 in for little r, I get big R squared, but it's being subtracted. So can I just log off the negative sign up front? And I think that's going to give me a positive 2/3 times my big R raised to the third power, and I'm going to integrate respect to theta. By the way, that gives me 2/3 times, let's get that differentiate. This becomes an r cubed theta. Multiplying r cubed by the theta value 0 is just going to be 0. I don't care. But with the r cubed theta times 2 pi, it's going to give me my r cubed times this. Oh, thank goodness. That is a 4/3 pi r cubed. Which is exactly what we want.
Why? I'm not following this.
It's flying from where to where?
There, from there, and then like,
From here to here.
oh, from the top to the bottom to that one. Okay.
Matthew, I didn't need to use any calculus. I was just cleaning up arithmetically. I was just simply saying I can cancel the 2's. I pulled the negative 2/3 out. That's all I did.
And then why did you put like evaluate at bars?
Because I skipped it up here, that's why it's confusing. Because this over here, I'm still evaluating from 0 to big R.
Okay, and why did you cut and you cross the bar?
Because I forgot to put the R in, so don't look at the from here to here. Let's forget the R. Did you guys know this? This was a good example in the sense that with the original triple integrals, it looks pretty nasty to evaluate. How about another one? You guys, I don't want to make these up out of thin air. So let me take a peek. I know I've created some examples.
Do we have a quiz today?
Yes.
Just making sure you don't forget.
Oh, trust me, I won't forget about a quiz.
That's so true.
So can I call this example 2?
That's true. Yeah, you got actually. We might actually get the quiz back on time.
I heard that. Jeez. Yeah, the beginning of this week, I completely forgot that Monday's a holiday.
Same here. What were you gonna teach us?
Moments. You guys, I made it central, but I did not provide a picture. You have to confess, looking at this integral, it looks relatively nasty in terms of all the sums and the squares in here, and that screams out at me the basic cylindrical coordinates is the way to go. However, it is now a question of changing, substituting in, rewriting everything in terms of z's, r's, and thetas. And to make a substitution, I can't do it without a picture first. So let's take a break. And before we change everything into cylindrical coordinates, so that I can change everything to cylindrical coordinates, what does the surface look like? So I can change my boundaries. What does the surface look like?
Can't
No,
see
no,
it.
no. It's irrelevant. To change bounds, I need to look at this region in three-dimensional space. Did you guys see my point? Let's concentrate on that region. It looks like I'm looking at z values ranging from this surface to this surface. Look at the bottom one.
Now say that again, the actual function right there.
I asked you to change these bounds of integration in terms of z's, r's, and thetas. What does the surface look like? And I wanted you to say, I don't care.
Why?
Because I think to change the bounds, the only thing that's important is what this surface looks like in free space.
Okay, because that's added force space something.
If you want to think of it that way,
Yeah.
yes, because I think everything, all the symbols combined in import, could be interpreted as looking at the amount of space within a four-dimensional object.
Okay.
However, if I were to take a peek at z being equal to the lower bound of integration, you guys, what does that
Is
look
that a
like?
general statement then? We ignore whatever's there when we're changing our bounds?
Absolutely.
Okay.
I think what's in the integrand's position is completely irrelevant in terms of your bounds of integration. That's why I asked that question.
Okay.
And you guys, check this out. What does that look like? I said, what does that look like? I asked. The what?
Cylinder cut in half.
It's a heavy. It's a cone. Well, you meant a half cone. So I think in three space. X-axis, y-axis. You guys are just going back to the surfaces. This the surface is in three space. Oy, oy, oy. Z-axis. I think it looks something like this.
So cool.
Whoa, so what about the upper bound integration? Whoops. Yeah, that's right. What does that look like? I'll close my pen, it's drying out. It's a hyperboloid?
Negative on this.
An inverted paraboloid. And so I think my surface looks like this. Yes. Well, actually, you guys, with my red arrow, this is really simply where my arrows are positioned, bless you, in the SY coordinate plane. Excuse me, SY coordinate system, not plane. Now let's talk about these values. Well, if y ranges from here to here, that's just looking at a. Well, what does the graph of y equals square root of the thing look like? Oh, don't answer my question. Don't. Man, I am just a mess today. I meant it to be subtraction, not plus. My apologies.
Just like
Now don't stall. What does equation y equals square root of step look like? Half the circle. And there's the lower half. So I think in the SY coordinate plane, if you're to project this curve of intersection down to the SY coordinate plane, I think I'm simply getting a circle, which by the way has radius 1. And then finally, my x values are ranged from 0 to 1. Oh shoot, you know what? If my x values are ranged from 0 to 1, I think my picture is wrong. What's wrong with that? It's only half of it. It's actually only the half that's living on the right-hand side of the on the front side of the YZ coordinate plane. So keep that in mind, that my image has the entire x code. We're just looking at the front half. Well, let's see if we can't translate into cylindrical coordinates. I think the bounds of integration simply tell me that z is going to be ranging from
R to 2 minus R?
very nice, because I think x squared plus y squared is just r squared.
Yeah, and I meant to say r squared, 2 minus r squared, not 2 minus r.
Very nice. So my upper bound is going to be 2 minus r squared. Well, you guys are already used to that, right? X squared plus y squared equals r squared. Y over x equals tangent of theta. How would you get x in terms of r's and thetas? X equals r times the cosine of theta. Likewise, y is equal to r times the sine of theta. Well, you guys, let's just keep going. I think I didn't leave myself enough room. Jeepers. What's this upper bound of integration going to be?
Square root of 1 minus R squared cosine squared theta.
You know, I guess you're right. It's just that when I look at the picture and I project down the xy coordinate plane, I think my r values are simply ranging from 0 to positive 1 because it's the unit circle in blue. And so I think these are my bounds of integration. What about my theta values? Where are they going to range from?
0 to pi since you only doing half of it.
pi over 2 to pi over 2.
You know, you're saying negative pi over 2 to pi over 2. I think that's fine, but since there's so much symmetry here, you guys, does it really matter how I allow theta to range? As long as it's rotated halfway through one full revolution. So I think technically speaking, it doesn't matter to start at negative pi halves or 0. I think it's more convenient to start here. Again, because of all the symmetry relative to the z-axis.
Because you're only doing half the.
I'm only doing half.
Where's 0 in terms of gradient, like pi, the theta?
Wait.
Is it this the x-axis there?
Those are gonna be.
We were looking at 3D.
Yeah, so I'm going to think of theta being equal to 0 as coming straight up the x-axis. And I know in the picture I'm wrong. It really should start at negative pi halves to positive. And I'm just saying, that's all the symmetry, who cares? Oh, shoot, there's something I missed. What about what's the integrand's position? What is that? I can't hear you. R squared. Do you guys agree? Do you guys mind if we don't finish? Can I just today build some integrals, set them up? Because I think with the anti-differentiation process, I'm just going to get a z, multiply the r squared by this. That's just a polynomial. The integration here is really, really easy. So can I just concentrate on setting up the integrals? Unless there is something complex, I'll finish.
So we're integrating from the initial one from dz dy dx. And then we go down
Yes.
to dz dr dθ.
As a matter of fact, I may not have said this in English, I'm suggesting, look at that integral. I think it's relatively nasty. I'm too tired to evaluate it. So if I convert to cylindrical coordinates, you have to confess that really is a piece of cake to evaluate.
Do we still, when we change it to your cylindrical coordinates, is it still dz dr dθ, and that isn't dependent on what our initial integration order is? So like if we did dz dx dy, it would still be dz dr dθ?
But I think if you're, are you asking me if I'm going to interchange these?
Well, from your original integration, if that was changed, like if instead of doing dz dy
I see
dx,
your point, I see your point. As long as I got the picture correct, then I don't have to worry about interchanging anything. Once I got the picture correct, I can go straight down to setting up my bounds of integration, or my order of integration, to be from z to r to theta. So I think once you get your picture set, it doesn't matter how this is set up, what order of integration you have. It's completely relevant once you get your picture.
It's just convenient that we start with both dz on both of them, because then we just pull straight from the first integral.
But I have to confess, if the ZZ weren't here, wouldn't I do the same thing though? I simply look at the picture.
No, I agree, I'm just saying, by starting with dz on both integrals, it's as simple as, plugging in.
I can see it. I can see it.
Yeah, if we didn't start with dz, we'd have to get it in terms of dz. Well, to make it easier, then we could just,
See, I disagree with that.
well, we don't need to, but
We don't need to at all.
it would be kind of easy, then we could just manipulate the first bounds in terms of r.
I don't know. I think it would be a complete waste of time myself. But that's just my opinion. How about something like this? How about, oh, I drew a picture. So I've got some region E in 3 space. In the integrand's position, I've just got y over x. I'm integrating respect to volume, and here's the corresponding image in 3-dimensional space. X-axis, y-axis, z-axis. Looks like it got a cylinder. Does cut off on top, not parallel to the xy coordinate plane. And here's the equation of the cylinder. Oh, you know what? In my picture, I've got something else. I have a plane sitting in here. How about I use the